Hello my scholars, you're welcome to my school YouTube channel and my name is Frank. In today's video we shall be learning about refraction of light. So relax, do not go anywhere and we'll be right back. You are welcome back to my school YouTube channel. In today's video, like I said earlier on, we shall be learning about refraction of light wave. But today we shall be dealing with the part 1 of it. So before we begin with our lesson, let's quickly run through the objective for today's lesson. So objective number 1, explain how the direction of light changes as it travels from one medium to another. 2, deduce a value of refractive index of a given material from measurements of angles of incidence and refraction. 3, explain the meanings of critical angle and total internal reflection, stating the conditions under which they occur. And the last but not the least, establish the relationship between critical angle and refractive index and apply it to the solution of simple problems. So let's begin with our lesson properly. So here we are simply going to look at what we mean by refraction. Okay, so refraction is a change in direction of light rays as the light travels from one medium to another media of different densities. Okay, so refraction is responsible for the following observation. One of them is the bottom of a clear stream or river appears to be shallower than it really is. Then 2, a rod partially dipped in water appears bent or broken. And 3, letters in print appear to be nearer to the eye when a thick glass block is placed over them. Okay, so don't forget that refraction occurs when light ray travels from one medium to another. So this medium could be from air to glass, or from glass to air, or from air to water. Okay, so consider a light ray traveling from medium A to B. So let's move to the next slide so that we can see the graphical representation of that. So this is a graphical representation of a light ray traveling from medium A to medium B. Okay, so let's simply explain what these letters mean in this diagram. So PO, which is PO here, represent the incident ray, which is the path along which the light travels in the first medium. So in this case, the first medium here could be air, okay, or the medium here could be glass, okay, but in this case, it is air. So I'm going to tell you the reason why it is air. Okay, then O arrow, which is from here to here, is the refracted ray, which is the path along which the ray now travels as it enters the second medium. Then we also have NOQ, okay, NOQ, okay, which is the normal. Okay, so the normal is a perpendicular to the plane surface of separation between the two media. Now remember that media is plural for medium. Okay, so medium is singular while media is plural. Then I here represent the angle of incidence. Of course, we know that that is the angle which the incident ray makes with the normal. Okay, then we have arrow. Then arrow there represents the angle of refraction, which is the angle the refracted ray, which is this, okay, makes with the normal. Okay, so the reason why I said the medium A here is air and the medium B here is glass, okay, is because of how the refracted ray is bent towards the normal. So this simply shows that medium B is denser than medium A. Okay, so that is just the simple reason. But as the lesson progresses, you will get to understand what's the statement I just made now. So let's move over to the next slide. Now, as the ray travels from medium A to medium B, the refracted ray bends towards the normal. Okay, and this is because medium B is denser than medium A. So meaning that if the light travels from the less dense medium, okay, to a denser medium, then the ray, that is the refracted ray, is going to bend away from the normal. Okay, so let's look at refraction of light at plane surfaces through triangular glass block or prism. Okay, so we can demonstrate the refraction of light at the air glass boundary using a rectangular glass block as follows. So this is just a diagram of the rectangular block, okay, glass block, right? And this is the incident ray. So this is the refracted ray, okay, which actually happened inside the block, okay, while this is the emergent ray. Okay, of course, the first interface here is the air, while the second is the glass. So let's move to the next slide to fully understand what is happening here. So procedure 1, a thick rectangular glass block ABC is placed horizontally on a drawing paper, fixed by means of drawing pins on a drawing board. Then the outline of the glass is drawn with a pencil. Then number 3, the glass is removed and the normal ON and the line PO are drawn as such that PO makes an angle I with the normal and the glass is replaced. A ray of light from a ray burst is incident on the glass surface AB along PO at an angle I to the normal. Then the ray is refracted in the glass block and emerges from the side CD along arrow X. So the points arrow and S are marked on the emergent ray. Then the glass block is removed and the line arrow S and O arrow are drawn. Also, a normal to the side DC is drawn at arrow. Then I is known, but the angles arrow and E are measured and recorded, while the lines arrow S is found to be parallel to the line PQ. The procedure is repeated for other values of I, provided they are all acute. In each case, arrow and E are measured and recorded as usual. Okay, so this is just a simple of what that diagram, just illustrating what happens in that diagram. More or less like trying to illustrate the glass prism experiment. Okay, so let's move to the next slide. So PO is the incident ray, O arrow is the refracted ray, arrow S is the emergent ray, then I is the angle of incidence, arrow is the angle of refraction, and E is the angle of emergence. Right, now let's move on. If the incident ray is along the normal O, NO, okay, so the incident ray actually incident normally on the plane surface here, okay, so that means the incident ray is at angle 90, okay, with the side AB, such that I is equals to 0. So when the incident ray, okay, is at angle 90 to the surface or to the side AB, okay, then the angle of incident in that case will be equals to 0. Then it passes straight through the glass emerging on the face CD without a change in direction. Then in that case too, the angle of refraction will also be equals to 0. So this is typically what this diagram is illustrating. So the angle of incident and the normal, they all lie on same straight line. Okay, so in that case, the angle of incidence is going to be equals to 0. And that same angle of incidence that was incidented on this surface, okay, that was incidented normally on this surface, is also going to pass out straight, okay, from the glass, making the angle of refraction also equals to 0. So let's move to the next slide. Now, yes, we are going to be stating the law of refraction. So just like the law of reflection, they are two in number. So the first one is similar to the first law of reflection. Okay, so the only difference is instead of saying reflected ray, you use the word refracted ray. Okay, so the first law says that the incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. While the second law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of medium. And this second law is called Snell's law. Okay, so if you are asked to state Snell's law, basically they are asking you to state the second law of refraction, okay, which says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. Okay, and this law is known as Snell's law. So mathematically, Snell's law is stated as sin I, that is sine of the angle of incidence, all over sine of the angle of refraction is equals to n, where n is a constant for a given pair of media. So the constant n is known as the refractive index of the second medium. Now, if light is traveling from air to glass, the refractive index of glass is given by, so the A then Ng here simply means that the light ray is traveling from air to glass, okay, and this represents the refractive index of the second media. So the medium here, the second medium here is the glass. So this is actually the refractive index of glass, okay. So mathematically, this is equals to sine of angle of incidence in air over sine of angle of refraction in glass. So let's move to the next slide. If light travels from glass to air, then the refractive index is given as, so this is A, okay, this is G, then NA, indicating that light ray travels from glass to air, and this is also equals to sine of angle of incidence in glass all over sine of refraction, okay, sine of angle of refraction in air. Right now, from the principle of reversibility of light, of course, in our previous lesson when we are talking about reflection of light waves, we actually stated this principle, okay. So this principle simply states that the path of light ray is reversible, okay. So from the principle of reversibility of light, we have that, so this indicates the refractive index of glass, right? So we can as well say reverse this to be equals to 1 over when light ray travels from glass to air. That is, here, this is when light ray travels from air to glass. It's now equals to when light 1 over when light ray travels from glass to air. Okay, so in refraction, there is a change in speed, direction, and wavelength. And the reason for that is because light is actually traveling it's traveling between two mediums, probably from a less dense medium to a denser medium, or from a denser medium to a less dense medium. So in that case, there will be a change in speed, direction, and wavelength. Okay, but remember that there's a relationship between speed, wavelength, and frequency. So if you find out very well, frequency is not measured. The reason why frequency is not listed here is because frequency remains constant. Okay, frequency depends on the source of light. So in this case, it remains constant. It doesn't change. Okay, now therefore, as light travels from air to glass, the refractive index of glass is given by, that is light traveling from air to glass, is equals to speed of light in air all over speed of light in glass. Okay, so but there is a relationship between refractive index and the sine of the angle of incidence. So this is it. When a ray of light is refracted from one medium to another, let's say from air to glass, then to water, their boundaries being parallel, their boundaries are parallel, then n sine I is equals to constant. Okay, that is the refractive index of air, then sine of the angle of incidence in air is equals to the refractive index of glass times the sine of the angle of incidence in glass is equals to refractive index of water, then times sine of the angle of incidence in water. Okay, so let's move to the next slide. Okay, so of course this meaning I've already explained them. So therefore Na, Ng, and Nw are the respective refractive indices of air, glass, and water. So let's just apply that formula there in solving this problem. So a ray of light through glass of refractive index 1.5 if the speed of light in vacuum is 3.00 times 10 raised to the power 8 meter per second, determine the speed of light in the glass. So to solve this question, we'll have to move over to the board to provide answer to this question. So first thing first, let's write out the parameters that are given to us. So n is given to us to be equals to 1.5. Okay, so remember here, light is traveling from vacuum, and vacuum here represents air, so we are having this. So this actually represents the refractive index of the glass. Okay, then we are told that the speed, so let's use x to represent the speed of light in vacuum, which is 3.00 times 10 raised to the power 8 meter per second. But remember that n, which is refractive index, is equals to speed of light in air, which is the same as vacuum, all over speed of light in glass. Okay, because in this question it was mentioned that we should determine the speed of light in the glass, right? So we know the refractive index to be equals to 1.5, right? And we know the speed of light in air to be equals to 3.00 times 10 raised to the power 8 all over the speed of light in glass, which is actually what we are looking for. So here we can just switch position, or if we cross multiply, it's still the same thing. So if we cross multiply, we'll be having 3.00 times 10 raised to the power 8 to be equals to 1.5 times the speed of light in air. So in this case, we can say let the speed of light in air be equals to x, right? So here we'll be having speed of light in air. So let's just put it here. Speed of light in glass, speed of light in glass is equals to, of course, these two we can switch position, right? So here we'll be having 3.00 times 10 raised to the power 8 all over, then you'll be having 1.5. Okay, so remember that if we divide 3.5 into 2, if we divide 3 into 2, that will give us 1.5. So 1.5 here is 1, then 1.5 here is going to give us 2. So we can say that the speed of light, the speed of light in glass is equals to 2.00 times 10 raised to the power 8 meters per second. So basically, this is how you apply these formulas in solving simple problems. So let's return back to the screen to continue with our lesson. So here we are going to be looking at real and apparent depth. Okay, it is observed that a mark on a piece of paper placed under a clear glass block appears nearer to the top of the glass block when viewed from the top. Now, this depth, as it appears to the eye, is called apparent depth. The actual depth of the glass block is called real depth. Okay, so the real depth, the apparent depth, and the refractive index are related by the formula. Refractive index is equals to real depth all over apparent depth. So let's move to the next slide. Now, experiment to determine the refractive index of block by real and apparent depth method. Okay, so this is our horizontal surface, and this is an object, that is lying straight on the horizontal surface, and this is the glass block, right? So from here you can see that the thickness of the block actually represents the real depth, right? While the apparent depth is how the object appears, to the eye when you view it from the block. Okay, why these are just the other apparatus that is needed for this experiment. So this is a cork and this is a search pin. Then this is your rector stand, just to hold the pin and the cork in position. Okay, so D, capital letter D represents real depth, small letter d represent apparent depth, while y represent apparent displacement of the object. So from here you can see the apparent displacement of the object as if the bottom of the horizontal surface actually raised, was moved up a little, to this point. So that height is actually what is referred to as apparent displacement of object, right? Why as you see the object, okay, the height that you actually see when you view the object from the top of the block is what you refer to as apparent depth. So this place appears as if it's actually the base of this block, or it's actually where this paper is kept, okay? But in reality, this is not where the paper is actually kept. So the distance y here is what you refer to as apparent displacement, okay? So let's start with the procedure. 1, a glass block is placed vertically above an object, so it could be a straight line drawn on paper as shown above. Then 2, the search pin is fixed to a piece of cork and held to the rector stand by clamps such that it slides up and down. Then 3, the search pin is then moved up and down until there is no parallel between it and the image of the object shown through the glass block from above. Let's move to the next slide. Now that is the search pin and the image of the object are aligned when viewed from above. Then the read depth D, apparent depth small letter d, and the apparent displacement y are measured. Okay, so let's move back to the diagram, the previous slide. So from here you can see that the read depth is equals to the apparent depth, okay, then plus the apparent displacement, okay, from this diagram. See, this is the read depth, while from here, this point to here is the apparent displacement, is the apparent depth, sorry, while from here to here, which is where the horizontal, where the object is, okay, is the apparent displacement. So you can see from this diagram that the read depth is equals to the apparent depth plus apparent displacement. Please, let's move back to the previous slide. Okay, so read depth is equals to apparent displacement, which is small letter d, then plus apparent depth, sorry, then plus y, which is apparent displacement. But remember that refractive index is equals to read depth all over apparent depth, which is capital letter D all over small letter d. Now remember that n represents the refractive index of the glass. Okay, so basically what we are trying to do here is just for us to derive a formula for calculating or for solving for apparent displacement, which is y, right? So from here, from this relationship, we decide to make we decide to make d, which is the apparent depth, the subject of formula, by simply moving y to this side of the equation, so that that d, okay, that small letter d is now equals to big letter D minus y. So in place of this small letter d, we'll replace it with d minus y, which is big letter D minus y, right? So that is why here, for our refractive index, we are now having d all over big letter D minus y. Why? Because our small letter d is now equals to d minus y, right? So at the end of the day, we now have d minus y is equals to d all over n. Why? Because these two have to switch positions since we are trying to make y the subject of formula here. So these two will switch position. So n will move to the position of d minus y, and d minus y will move to the position of n. Okay, so that at the end of the day, we now have d, which is capital letter D minus y is equals to capital letter D all over n, right? So since we want to make y the subject of formula, right? So we can decide to move this minus y to this side of the equation and it becomes positive. Then we move this d, capital letter D over n, to this side of the equation and it becomes negative. So that at the end of the day, we're having d minus then d capital letter D all over n. So you can do it. If y is equals to x, it also means that s is equals to y. Okay, so here y is equals to d minus d all over n, right? So here we can decide to solve this small fraction. So to solve this small fraction, this d here is also over 1. So that the LCM of 1 and n is equals to n. So 1 divided by n, that will be equals to n. Then n times d, that will be dn. Then this minus sign, then minus n divided by n, that will be 1. Then 1 times d is equals to d. So if you check these two, values very well, okay, there is something common between them, which is d. So if we factor it out, we'll be having d outside, then bracket open n minus 1, right? Because if we use this d to multiply everything inside this bracket, which is n minus 1, it's going to return us back to dn minus d, right? So y is now equals to d bracket n minus 1 all over n. So this is the formula, okay, that we use for calculating apparent displacement if we are asked to. But remember that ds stands for the read depth, okay? So in the case of glass, that represents the thickness of the glass, while n here stands for the refractive index of the glass. Okay, of course, these two n are distinct. They represent the refractive index of the glass. Y here represent apparent displacement. So let's move over to the next slide. Okay, so we are going to apply those formulas which we've just derived now into solving some simple questions. So let's begin with question 1. A rectangular glass prism of thickness 12 centimeters is placed on a mark on a piece of paper on a horizontal bench. If the refractive index of the material of the prism is 1.5, calculate the apparent displacement of the mark. Okay, so to solve this question, let's move over to the board to do just that. So first thing first is for us to write out the parameters that are given to us in the question. So one of them is the read depth, which is D. Okay, so in this case, the thickness of the glass represents the read depth. Okay, and that is 12 centimeters. Then we are also given the refractive index of the material to be equal to 1.5. Okay, now remember we just derived the formula for calculating apparent displacement, which is y is equals to d. Okay, in some cases, some authors prefer to use r in place of d, but it doesn't matter. Whichever one you use, just make sure that you know what the letter that you use represent. Okay, so d bracket open n minus 1 bracket close all over n. So this is the formula we use to answer number 1 question. So here we just substitute our value since we are looking for y. So write out our y, then equals to, then in place of d, we replace it with 12, then bracket open, our n is 1.5, then minus 1, bracket close all over 1.5, right? So let's deal with the denominator first. So if we subtract here, that is 1.5 minus 1, we'll be having 12 bracket 0.5. But remember that bracket represents multiplication all over 1.5. So 0.5 is the same thing as 1 over 2. Okay, so here we can write 12, then times 1 over 2 all over. While here, 1.5 means 3 over 2. Okay, so here we use 3 over 2. Now, the essence of this is just so that we can solve this without using calculator. Okay, so 2 here is 1 and 2 here is 6. So 6 times 1, that will give us 6. So we now have 6 all over 3 over 2. Okay, so let's put this. Of course, remember that this fraction sign here, this divisor here, simply stand for divide. So here we have divided 6 divided by 3 over 2. So it's still the same. So here we're having 6 over 1. Then we change this to times, then invert the second fraction. Because remember that 6 over 1 is still the same thing as 6. So nothing has changed here. So here we'll be having 2 all over 3 so that we can divide easily. So 3 here is 1 and 3 here is 2. 2 times 2, that will give us 4. Okay, so in this case, the apparent displacement is equals to 4 centimeters. So let's return back to the screen so that we can solve example 2. Okay, so for example 2, we are told that a nail is placed at the bottom of a bucket, which is filled with water to a depth of 20 centimeters. At what depth will the nail appear to be when viewed from the top? So we are told here that the refractive index of water is equals to 1.33. So this depth that they are asking us about, okay, is actually they are asking us about the apparent depth, right? But remember that the relationship between refractive index, read depth, and apparent depth is given as n is equals to read depth all over apparent depth, right? So from here we can just switch position between apparent depth and read depth. Of course, you can't switch position. If we are calculating for read depth now, you can't switch that position, so you just cross multiply. Right now, in this case, we will also cross multiply, but we are just trying to make it faster, right? So we just switch position between refractive index and apparent depth, just switch position. So apparent depth takes the place of refractive index, and refractive index takes the place of apparent depth. So in that case, we've actually made apparent depth the subject of formula. So the apparent depth is now equals to read depth all over refractive index. But remember, in this question, we were told that the bucket is filled with water to a depth of 20 centimeters. So that depth of 20 centimeters actually represents the read depth, right? So in place of read depth, we just fix 20 there, then divided by the refractive index of water, which is given to us to be 1.33. Okay, so that apparent depth is now equals to 20 divided by 1.33, and that will be equals to 15.04 centimeters. Okay, this is the depth at which the nail will appear, okay, when viewed from the top. So this is where we bring the preview of today's video to a close. I believe you enjoyed it. You can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. Now don't forget that in the complete video you will learn about total internal reflection and critical angle. You will learn about how to derive the relationship between refractive index and critical angle, and also use this formula to solve simple problems. You will also learn about optic fibers, okay, and its application, and many more. So I believe you enjoyed the preview of the video that you've just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.